Yeah. Hi all. Good evening and welcome to the 12th and last week of the live session for AI SMPS. Um, can you hear me properly and is my screen visible? Can you just confirm? Hello. Am I audible? Okay, so I'm going to assume that I'm audible and I'm going to continue with the session. Um, Please feel free to let me know in case there's any issue with the audio or the screen sharing. So first of all, thank you for waiting for. I was late by a few minutes, so sorry for the delay and thank you for waiting. And yeah, like I had said last week, we'll begin a bit early today because I have another urgent meeting to attend later in the evening. So yeah, with that said, um, let's get started with the questions for today. So today we are going to discuss some questions related to week 12 content, which is basically related to constraint satisfaction problem. And towards the end, we are going to briefly go over some of the doubts that were uh, recurring doubts that came up in the past few live sessions. Again, if we have time. And yeah, that's about it. So yeah, let's get started with the questions for today. All right. So before we get started, uh, this is the first setting for the question that we're going to deal with, the first few questions. So this question deals with a crypt arithmetic puzzle, which is basically an arithmetic problem in which the numerals have been uh, replaced by letters. Okay. So take a simple example of addition of two numbers. So instead of numbers, these numbers are now represented by some letters which happen to be letters from the English language, right? So each numeral or each number is assigned a distinct letter, and each letter stands for a unique numeral. So there's a one-to-one mapping between letters and numerals. And every number begins with a non-zero numeral. So one thing to note is that no letter can be assigned zero. Basically, it has to start from one or above, right? So our task is to find out an appropriate assignment of these letters to different numbers such that this equation holds. Okay. So a given equation may or may not have a solution, right? So you have to keep that in mind as well, or it may have one or multiple solutions. So that is another thing that we need to keep in mind, and that's it about the problem setting, about the crypt arithmetic puzzle. And so here we are given one crypt arithmetic puzzle, which is basically jab plus jab equals to good. So what we have to do is we have to find appropriate numbers that can be uh, said to be represented by these letters given in these words over here. So for example, J could represent a particular number, like let's say 8 or 7, right? So I'm giving you a hint over here. Similarly, A and B could also be representing different numbers, and we have to find a particular assignment of these letters to some specific numbers such that when we replace the letters with the corresponding numbers, this equation will still hold. Okay, so that is the equation that you basically have to solve. And okay, so I hope the problem setting was clear. Um, no, Abhishek. Okay, thanks for confirming, Rocky. And yeah, no, Abhishek, you didn't miss anything. Good evening. So we just started, and this is just the first question that I was displaying. Um, Basically, we have to go over this. We have to solve this crypt arithmetic puzzle. Okay, so I'll give you a couple of minutes to. Yeah, no worries about it. Network issues might happen at my end also sometimes. So um, I hope the problem setting is clear for this first question. Um, I'll give you a couple of minutes to maybe go through the setting once more. If there are any doubts, we can again discuss it, and then um, okay, sure. I'll just repeat the setting once more. So basically, the first question deals with solving the script arithmetic puzzle, um, which is basically it's like an encryption. Okay, so you're given this equation over here, like jab plus jab equals to good. Okay, the encryption or the encoding over here is that each of these letters J, A, B, and G, and O, and D, these all represent some numbers which is greater than or equal to 1. Okay, and each letter is assigned to one unique number. Okay, and one unique number is assigned to one unique letter. Okay, so there's a one-to-one mapping between the letter and the numbers, and you have to find appropriate assignment of the letter to some numbers such that this equation holds. For example, if you replace the letter with the number counterpart, the equation should still hold. So you have to find such an assignment of such a mapping of letters to numbers. That's what the question is about. So I'll give you a couple of minutes to try to solve it, and then we can have a discussion. Hi, can you please mute yourself if you don't have a question? Yeah, thanks. Thanks a lot. Sorry about that. Yeah. So if you have a, yeah, partial solution, you can feel free to share it in the chat box as well in the meantime. Okay, so I'll give you some easy examples to begin with. Okay, suppose let's consider a much simpler cryptarithmetic puzzle. Okay, suppose this is the puzzle that you have to solve. Okay, a plus a equals to cd. So basically, you have to come up with an assignment for a, c, and d such that um, this equation holds. So suppose you assigned a to be 2, right? Then a plus a, which is 2 plus 2, would be equal to 4. But as we know that this equation requires the number on the right hand side of the equation to be a 2-digit number. So definitely a equals to 2 is not a good assignment or not an appropriate assignment, right? So we have to think for some other assignment to a. So what do you think could be a proper assignment to a that would make this equation true? 5, yeah. 5 could be one assignment, but remember that there was one more condition that uh, any any letter is assigned a number that is greater than or equal to 1. So if you assign 1, if you assign a is equals to 5, you will have 10. Exactly, yeah. So we have to take something more than 5. So for example, let's say we take 7, right? So 7 plus 7 gives us 14. So in this case, A is assigned 7, C is assigned 1, and D is assigned 4. So this is one proper solution to this puzzle. Similarly, there could be other potential solutions as well. We could have 8 plus 8 or 6 plus 6 as well. Each of these would have different assignments to A, C, and D. And so there are multiple solutions possible to this particular cryptarithmetic puzzle, right? So this is one simple example. Let's take another example, which is if plus it equals to y. So can you think of a possible solution to this particular cryptarithmetic puzzle? I'll also give you a hint. So both i's will be assigned the same number. Let's say we assign 9 to them. Okay, this looks like a bad 9. Let me rewrite it. And let's say we assign 2 to f and 3 to t. Then what will the sum of these two be? So is this a proper assignment? Yeah. Uh, so Abhishek, there can be multiple solutions or there can be no solutions as well. Usually you will be given a certain domain that your letters have to follow. So because of that domain, your problem simplifies. So you have to make a guess from a limited set of possible solutions. Yeah, so basically you have to make a guess so that this equation is satisfied. But yeah, the guess that you have to make from would be from a finite or a limited set. So that makes the problem a bit simpler for you. Yeah, and as some of you suggested, 82 plus 83 and 91 plus 92, these are also possible uh, solutions. So again, there are multiple solutions to this particular problem as well. So coming back to our jab plus jab equals to good. um, Do you think there could be multiple patterns or multiple, not patterns, multiple solutions? 943 plus 943. Yeah, that's a good solution. That's actually a correct solution as well. Um, so let's look at what could be the possible solutions. And as some of you pointed out, 943 plus 943 is in fact one of the solutions. So there will be three solutions to this particular cryptarithmetic puzzle, and there are three solutions only, because any other assignment you won't be able to come up with an appropriate representation. That that holds true for other for this particular equation. I think there are three solutions only, but yeah, you can verify yourself as well. Another solution could be 832 plus 832, and a third solution could be 723 plus 723. Okay, and each of them assign a particular number to each of these letters. Okay. Um, any doubts on the solutions? I'll give you maybe 1 minute or 1 or 2 minutes to convince yourselves, and then we'll quickly move on to the next few questions. Yeah, Rocky. So essentially, this is based on guess, but you can make some intelligent guess. Okay, so you don't have to make a random guess, and that intelligent guess or informed guess will be based on the problem domain that is given to you. Okay, so you're given some information in this problem setting, some information which is some of these information that can be helpful is that each numeral has a distinct letter assigned to it, and each letter stands for a unique numeral. So this is one fact, you know, that there is a one-to-one mapping between numbers and letters. So this is one fact that you can use. So when you assign a particular number to, let's say, one alphabet, let's say you start by making a guess that J could be 7, then you know that neither of A, B, the none of A, B, O, and D or G would have the same number assigned to them, right? So that is one thing that will reduce your possible set of solution that you can guess from. Another information is that 0 cannot be one of the assignments, and then yeah, it is essentially a guessing game only, but kind of an informed guess with some constraints, exactly as pointed out by Namita. Yeah, that's correct. Okay, so yeah, sorry about that. So yeah, let's have a look at some of the questions based on these. So if you have understood the solution, then these will be pretty straightforward to answer. So does the above puzzle have a unique solution? B. Yeah, we know that it has three solutions, so definitely it doesn't have a unique solution. So the answer would be no. Okay. Is the value for the letter G unique for the above puzzle? Um, and what is this value? If your answer is yes, and if it's not unique, then you can enter nil. So what do you think about that? Given the solution over here, it is unique, right? So even though the overall solution is not unique, there are some letters that you know that will definitely have a certain value assigned to them. Otherwise, we won't be able to um, satisfy this particular equation. So yeah, G has a unique value assigned to it, and that is 1. Okay, this was also straightforward. And is more than one value possible for the letter J in different solutions? And as we saw, this is possible, and so answer would be yes. So good question, Abhishek. What is the use of arithmetic puzzle? So this is essentially a sort of a toy example, or a very simple problem to introduce you to the idea of constraint satisfaction or constraint restricted problems. Um, there are more advanced or more complex applications of similar problems. So for example, here you have a very simple equation like jab plus jab equals to good. Consider you have a very complicated equation, some huge cryptographic example or a problem statement where you have a very large string, and each of those letters or each of those characters could be assigned a particular another character, and those you have to kind of break that encoding, or you have to form a appropriate encoding for that. Those are some areas where this could be applied. Of course, there can be many other applications, but yeah, you are I'll encourage you to explore more about that in your free time. Yeah. Yeah, so the solution to this will be yes, there can be more than one possible value for the letter J. Also straightforward. Okay, fourth question. What can we say about the value for the letter D, which is the last letter in the right hand side of the equation? What do you think will be the appropriate choice over here? B. Yeah, that is right. It can only always be an even number because irrespective of whether, so that will be, so this is the value that D takes will essentially be decided by the sum of the values that B takes, right? So irrespective of whether B takes a odd value or an even value, we know that the sum of two same numbers, where irrespective of whether it's odd or even, is going to be even, right? So D will always be even. Okay, so this was also pretty straightforward. Um, what about letter O? B. That is true. Following the same logic, it can also always be an even number. Again, pretty straightforward. So yeah, so these were the questions related to this crypt arithmetic puzzle. Um, before we move on to the next few set of questions that will be based on our consistency, um, I'll wait a couple of minutes to see if any doubt exists for these last few questions that we discussed, and then we can, after a couple of minutes, we can move on to the next question then. How many variables were present in the question? So the number of variables in this particular question, you could say that each letter is a variable, right? You need to find an appropriate configuration or a or an appropriate map of letters to numerals. Um, so each letter is a variable in this case, right? And your domain would be the set of numbers from which you can assign each letter a particular number. Yeah, here six essentially because you have JABGOD. Yeah, so six. Can you carry digits in this? Um, what do you mean by can you carry digits in this? I mean, we are doing some simple addition only, right? So I guess it depends on the way your problem statement is defined. I think the way this problem statement is defined, um, you have to restrict your answers to the assignments that will satisfy this equation. If um, if let's take an example where a carry would happen, um, would there be an assignment of jab where the carry could happen? Okay, an assignment is a case where we have to solve for the case where carry digits are zero. Okay, then that problem might have been defined in a different fashion. I haven't seen the question, so I can't comment on it. Um, but yeah, like I said, I think the way you would find solutions would be defined by the problem statement or the way the equation has been defined. Here, I don't think you can have an assignment as well as have those kind of a carry digit kind of uh, things going on over here. For example, if you assign, let's say, B as 9, um, can you find an appropriate assignment to A and J that could still satisfy good? We can't find it, right? So I think this equation itself restricts us to cases where those kind of issues will not happen. If it's defined, if a problem statement like you're saying in your assignment is defined where some carry digits are also involved, then you'll have to look for appropriate assignments for carry digits as well, I would say. But yeah, I'm saying this solely based on what you have written in the chat box. I haven't gone through the question myself, so yeah, have a more in-depth look at the question, and maybe that will be helpful to solve the question. Okay, so I hope there are no further doubts in the crypt arithmetic puzzle problem. If there are, please let me know. For now, let's move on to the next few set of questions, which will be based on this R consistency problem. Okay, so for what is R consistency, I would encourage you to have a look at the video lectures. There it has been explained in a very good manner. Um, so here basically what you are given is you have a constraint satisfaction problem. You have a CSP with three variables x, y, and z, and the domain of each of these x, y, and z is 3, 4, 5, 6. Okay, with all the three variables have the same domain, which is given over here. So this basically means that each of x, y, and z can take values from these four numbers only. Okay, and the way these numbers will take values would be decided by some constraints. Here we have two constraints. So there is one constraint between the variables x and y, which says that x has to be less than y. So whichever number you assign to x, um, that has to be less than the number you assign to y. And similarly, the constraint between y and z is that you have to assign a number to y that is less than the number assigned to z. And what we have to do is we have to find what would the domains look like after network is made R consistent. Okay, and we also have to draw a matching diagram because that will help us finding the solution, and then we have to write our answers in a particular fashion. So yeah, I'll give you a couple of minutes to kind of go through the question that is given, and you can try to solve it, and then uh, yeah, after a couple of minutes we can have an in-depth look at the solution or how to solve this particular problem. So any partial solutions, any approaches that any of you would like to share? Okay, so we already have a solution. Domain of x is 3, 4, y is 4, 5, and z is 5, 6. Um, yeah, I think that's correct. But what do the others think? So essentially what we can do over here is we can use the concept of arc consistency that was taught in the lectures, right? So the way we can begin is, let me move to the Jamboard. Yeah, if we revisit the definition of arc consistency, it said something like this. So a variable x is said to be arc consistent with respect to a variable y if and only if for every value of a in the domain of x there is a variable b in the domain of y such that that relationship or that constraint is satisfied. Okay, and we can use this revise x comma y to revise x comma y in one direction and revise y comma x in another direction to achieve this arc consistency. Okay, so this is a snippet from the video lectures, but to make this example more concrete, we can start by make this kind of a mapping diagram. Okay, so we can draw the domain of each of these variables, and to begin with or to start with, each of these domains will have all the numbers assigned to these mappings or these individual domains, right? And the next thing that we can do is we can make arrows to mark the constraints or the relationships between the different variables. So if you remember, the first relationship was x has to be less than y, right? So we will link each of these numbers to the corresponding numbers in the domain of y that satisfy this constraint. So 3 is less than 4, so there will be an edge between or arc between 3 and 4. There will also be an arc between 3 and 5 and 3 and 6. Similarly, there will be an arc between 4 and 5 and 4 and 6 and 5 and 6. There will be no arc from 6 because there is no number in the domain of y that is greater than 6. Right? Similarly, there will be, let me use a different color for this. There will be arcs between y and z also where the constraint was y has to be less than z. Right? So 3 will be connected to 4, 5 and 6. 4 will be connected to 5 and 6, and 5 will be connected to 6, and 6 will not be connected to anything else. Right. Now, what we have to do is we have to, okay, we have another solution. That's great. Um, I think both of you are correct. That's good. Or partially correct, maybe. Let's have a look at the solution, and we'll arrive at the solution also. So what we can do is we can use we can look at each of these numbers in the domain of x to begin with. Okay, and let us see that which of these assignments of these numbers to the variable x would not satisfy the arc consistency definition. Okay, so let's first look at the consistency between x and y. Okay, so here we see that this number 6 is not connected to any number in the domain of y, right? And if we revisit the definition of this variable of arc consistency, variable x is said to be arc consistent with respect to variable y if for every value of a in the domain of x there is a value b in the domain of y such that the constraint is satisfied. And we see that 6 here does not satisfy that condition, right? Because there is no value in the domain of y that satisfies this particular constraint, which is x less than y. So we will delete this. Okay, so we will delete this using this revise operation. Okay, you can have a more detailed look at it in the video lectures, but basically um, We will first look at at which are the variables that we can apply the revise operation, or which are the values that the variable x and y can take, that we can delete using the revise operation in x to y direction and then y to x direction. Okay, so we looked at the x to y direction and we deleted 6. Now let's look at the y to x direction, and we see that 3 is a number over here that is not connected to any number in the domain of x. So we will remove 3 as well. Okay. Now similarly, we will have a look at the relationship between y and z. So again, this 6 is not connected to any number in the domain of z. So we will delete this 6. And again, looking at the backward direction from z to y, this 3 will also be deleted because it's not connected to any number in the domain of y. So what we are left with now is a subset of this. So let's draw our mapping diagram once more. So this time we are left with 3, 4, 5 in the domain of x. We are left with only 4 and 5 in the domain of y. And we are left with 4, 5 and 6 in the domain of z. Again, let's draw the mappings. Okay, so I hope it's clear as of now. Any doubts till now in the process? Okay, that's great. So let's draw the edges for this mapping diagram again. So 3 will be connected to 4 and 5, 4 will be connected to 5, and 5 will not be connected to anything. And similarly, this 4 will be connected to 5 and 6, 5 will be connected to 6. Okay, so again, we'll have to do some deletions. First, in the x to y direction, we see that 5 is not connected to anything, so we remove 5. And here we see that both 4 and 5 are connected to something in x. Okay, so this from dy, nothing will be deleted. Now let's look at y to z. Again, nothing from y will be deleted, but from z, this 4 will be deleted because this is not connected to anything in y. Okay, so again, let's draw our mapping diagram with these deletions taken into effect. So here you have 3 and 4, 4 and 5, and 5 and 6. And let's draw the arcs once more. So 3 will be connected to 4 and 5, and 4 will be connected to 5, and 4 will be connected to 5 and 6, and 5 will be connected to 6. So now, do you think is the system arc consistent? Can we perform any more deletions? We can't, right? Yeah. So we can't perform any more deletions because we have reached an arc consistent stage. We see that all the uh, variables in the domain of x have some mapping to some variable in some value in the domain of y, and same for y to x and y to z and z to y, right? So we have reached an arc consistent state, and yeah, so the final solution is 3, 4, 4, 5, and 5, 6, as some of you already shared in the chat box. So yeah, I'll go back to the question and show the solution, and then so these are some questions based on this problem itself. We can have a look at it, but first I'll let you. Uh,
Sir, you started the class quite some time back.
yeah, so as I had said in the last live session, today we'll start a bit earlier because I have an urgent meeting later in the evening. So we started around, I think, 5:15 or something. But yeah, the session is being recorded, so no worries if you missed it. It will be
Okay.
made available.
All right. Okay. Thank you.
Yeah. Yeah, thanks for asking, and also thanks to all of you for adjusting for my meeting later in the day. Uh, yeah, that's about it. Um,
What time it is going to end?
I think sometime around 7 or so.
Okay.
Yeah.
Okay. Right. Thank you.
Okay. So Abhishek has requested for another explanation. So okay, let's go through it once more. So basically, what we had to do in this question is we had to find some particular assignments to um, x, y, and z from this given domain of 3, 4, 5, 6, such that these two constraints are satisfied. Okay. And one way to do that is through constructing these mapping diagrams, and using the arc consistency method or the revise operation that you may have seen in the lecture videos. And we start by drawing these domains for each of these variables represented by all the values that the variable can take initially, right? Which is 3, 4, 5, 6, 3, 4, 5, 6, 3, 4, 5, 6. We connect each value to between x and y or y and z that make this constraint satisfied, right? So for example, the constraint between x and y is x less than y. So 3 will be connected with an edge to all the numbers that makes this x less than y or 3 less than y satisfied, right? So 3 is less than 4, 3 is less than 5, and 3 is less than 6. So 3 will be connected to 4, 5, and 6. Similarly, 4 is less than 5 and 6, so 4 will be connected to 5 and 6. Similarly, 5 will be connected to 6, and 6 will not be connected to anything because 6, there is no number in 3, 4, 5, 6 that is greater than 6. Okay, so that's about x and y. Similarly, between y and z, there is another constraint, y less than z. So you will also have similar edges over here. 3 is less than 4, 5, 6. So 3 is connected to 4, 5, 6. 4 is connected to 5 and 6. And 5 is connected to 6. And 6 is not connected to anything else. Uh, right, I just realized that I was not sharing the Jamboard. Sorry about that. But yeah, I hope that's it's still clear. Okay, so once we have drawn the edges, now we will look at the revise operation. Basically what that does is we'll look at each of these constraints between these variables in this direction first, and then back in this direction. Okay, so what that will do is for every value in the domain of x that is not satisfying the arc consistency condition, we will delete that particular value. Okay, and what is the arc consistency condition is that there should be a one to at least one member in the other domain that this number is related to or linked to, right? And here we see that 6 is not linked with an edge to any number in the domain of y, right? So we will delete 6. This was the operation in this direction. Now we will look at this direction, y to x. And here we see that this 3 in dy is not connected to any number in dx. So we will remove that. Now we are done with dx and dy. Now we will look at dy to dz. And you'll see that 6 is not connected to anything in dz. So we'll delete 6. And then we'll see that in this direction, 3 is not connected to anything in dy. So we'll remove this 3. Now we have deleted a few elements from the domain, so we will redraw our mapping diagram with those deleted elements removed, and we will again make them edges and again follow the same procedure. And after doing a multiple such operations, we finally arrive at this particular state where all the where this is basically an arc consistent state, which basically means that for every value in the domain of x, there is a corresponding value in the domain of y to which it is linked, and similar for y and z, right? So we say that our problem is now arc consistent, and this is the final solution. So I hope that helps with the explanation. I'll let you try to work out the solution yourself, and I'll give you a couple of minutes, and then we can have a look at the next few questions based on this particular problem that we just solved. Um, yeah, so I've already shared the set dx, dy, and dz, Dr. Preeti. So I hope that helps. And to address your question, where till when will you share? So these slides have already been shared in the drive folder. If you are referring to that, um, yeah, definitely. So your assignment due date for week 12 is when? Can you tell me? Will it be this Wednesday, the coming Wednesday? So definitely before that it will be shared. I will try to get it uploaded tonight itself, but if not tonight, then tomorrow morning for sure. So before Wednesday, you will have access to the recording for sure. Um, okay, Ram. So I'll try if we if we have time, we can have a look at the 12th question from week 11. But let's see. Let's first cover some questions from today, and then if we have time, we can have a look at uh, these doubts. Okay, so any doubts in the solution till now? Sure. Can you maybe please mute yourself, um, if you, in case you don't have a doubt. Thank you. Yeah, sure. So let's go over how we got t, y, and z, t set. So yeah, essentially you're right, Abhishek. We made three graphs, and the way we got dy and dz is basically you start with the domains of x, y, and z, right, which are the same basically. You're told that these variables x, y, and z, they all can take values from amongst the numbers 3, 4, 5, and 6. So that is what is essentially represented by this dx, dy, and dz. And then you connect the corresponding values whichever satisfy a constraint, given constraint. Here it's x less than y and y less than z. Then you look at each element of dx that is not connected to anything in the domain of y or dy, and you delete that. And then you do the same thing in the reverse direction from y to z. You look at some element in y that is not connected to anything in x. You remove that. So that removed 3 from dy. You do the same thing in y to z direction and z to y direction, and then that ends up with you having deleted some of the elements from each of these domains, right? So you reconstruct the graph again, and you again draw the edges, and you again repeat the same procedure until and unless your system becomes R consistent. That's the whole point of the question. Okay, so let's now have a look at some of the questions based on this problem. And the questions are, for the above CSP, the value of dx after the network is made R consistent is, so what would this be? What do you think? It will be 3 and 4, right? Because we just saw that, yeah, 3 and 4 is the solution to the R consistency. So 3 and 4 will be the values of dx. Similarly, what will be the value of dy? That will be 4 and 5, right? And what will be the value of dz? That will be, what do you think would that be?
5.
5 and 6. Yeah, that's correct. Yeah. So these were some questions based on our consistency that we saw. So before we move on to some of the uh, doubts from the previous live sessions, there were some other questions also from week 12 that I wish to discuss.
What is the arc consistency physically means here? What is an arc here? It's
An
an
arc is
edge
the
is
edge. Yes,
edge is called as an arc.
yes, the edge is an arc, and you want to make the system you want to make your system basically, yeah, the problem consistent with all the constraints that are given to you. So in layman terms or in simple terms, that is what you want to do by achieving arc
Constraints here
consistency.
are x less than y and y less than z is the constraint.
Yes, yes, those are the constraints.
By doing that, what we get?
You get a solution to arc to this constraint satisfaction problem, right? This is a CSP that is given to you. You want to solve it. You want to have or come up with appropriate values that these variables x, y, and z can take that also satisfy the constraints given to you. So that's what you're trying to do essentially.
So, by making everything arc consistent, what does that graph conveys?
Uh, I'll encourage you to try to draw the graph and then see that if is there any value in the domain of x or y or z that does not satisfy the constraint. Okay, so if you do that, you'll see that after achieving arc consistency, there is no value in x, y, or z that violates this arc consistency, which basically means that x can take any value of 3 or 4, y can take any value of 4 and 5, and z can take any value of 5 and 6, right? And that could be potential solutions to your problem. That is what you are trying to achieve.
Okay,
Yeah.
all right. So,
Hello,
Okay.
sir. Now, what is on the screen that is based on question 6, 7, and 8. The
Um,
can you show the question 1 and solution that is fine, sir? I will screenshot that
Saundari,
my answer to the
I'm
question.
sorry to interrupt, but your voice is very uh, it's not audible properly. Can you maybe speak closer to the mic, or
Mm. Now is it audible, sir?
it's better, but it still has a few cracks in it. Um,
Okay, now what is on the screen that is based for question 6, 7, and 8? I understood the concept.
uh-huh.
Can you just show what is question 1 to 5 and just a question? I will make screenshots just
uh,
for 1 minute, just to show the questions, sir.
yeah, I can do that. But also to mention that these slides have already been shared in the Google Drive folder, so you have the slides and the solutions also accessible to you. So yeah, but still, I'll just show the questions 1 to 5.
Thank you, sir.
Yeah. So because the screen that I'm sharing currently, that is actually from the Google Drive folder itself. So before every live session, the slides are already uploaded in the Drive folder. So you don't need to worry about the questions. They are already available to you. The recordings will be made available by tomorrow morning latest. Okay, so questions 1 to 5 basically dealt with the script arithmetic puzzle where you had to find something similar to this constraint satisfaction problem that you just saw. It was much simpler here. You just had to have given this particular equation like jab plus jab equals to good, and you had to find appropriate assignments of numbers to these individual letters. And also, those assignments followed certain constraints that are given to you in this particular paragraph over here. I won't go through all of them. You can just have a look at it later. And yeah, basically you had to follow those constraints, come up with appropriate assignments to of numbers to these letters, and find appropriate solutions that satisfy this equation. Right. So that's all you had to do. And questions 1 to 5 were just based on the solutions that you came up with for this particular equation. Okay. So now that we are done with this, let me move on to another question that I wanted to discuss, which is based on select value forward checking. So this is another part of um, week 12 content, and you might notice that I have taken a simple screenshot. So try not to look at the answer that's already given over here. Try to solve it on your own, and uh, yeah, we can we can discuss the solution in detail. But yeah, I couldn't remove this while taking a screenshot in a hurried way, so sorry about that. But yeah, try not to look at the solution first, try to solve it, and then you can have a look at the solution. So this basically tells us that we are given a map coloring problem with 6 regions A, B, C, D, E, and F. Okay, so in case someone is not familiar with what that is, you have different regions and you need to assign different colors to those regions, such that so suppose this is a region, uh, this is another region, this is another region, so on and so forth. Yeah, you could think of these as countries in a map, right? And if you had to assign a color to each country, let's say the colors are amongst R, G, and B, which is red, green, and blue. If you assign some, let's say some R2 over this, this map coloring problem, what it states that any adjacent area to this area that is assigned R cannot be assigned R again, right? So this has to be either G or B, and this has to be either G or B, right? Similarly, the same holds for any area, right? So you have to find appropriate coloring assignments to these individual areas such that no two adjacent areas have the same color. That is what it is. And so you are given 6 regions A, B, C, D, E, and F, and you are processing them in a particular order that is that is also already given to you, right? So you're processing them in the order of A to A, B, C, D, E, and F, which basically means that you assign a color to A first, then B, then C, then D, then E, and lastly F, right? And the domain of all the 6 regions is RBG, which basically means that all of these regions can take either red, blue, or green as their colors. Okay, and yeah, so what you have to do is you are given that these regions are adjacent to each other. Okay, so that information is given to you. A and B are adjacent, A and C are adjacent, A and D are adjacent, B and C are adjacent, C and D are adjacent, C and E are adjacent, D and DF are also adjacent. Okay, so this is also given to you, and you have to use a generalized look ahead algorithm with select value forward checking to solve the map coloring problem. And you are given a particular partial assignment to begin with, so you don't have to start with a random guess. You are already told that region A has been assigned R and B has been assigned blue. So you have to come up with potential assignments to all the other regions such that this consistency holds and the map coloring problem is also satisfied. Okay, so I'll give you some time to try to solve this on your own, and then we'll have a look at the detailed solution. All right, so we can, so I see some of you have shared partial solutions. Um, yeah, so we can have a look at the solution now. So what the first thing that we can do is we can draw this connection diagram that is given to us, right? So we have three regions or six regions, A, B, C, D, E, and F. Let's draw how each of these are connected to each other. Okay, so this is A. Okay, each of these can take either of R, G, and B. So let's write that down. Okay, so this is what is given to us, and also let's connect the different regions that are connected to each other. So A is connected to B, then A is connected to C, and A is connected to D. Then we have B is connected to C, we have C connected to D, and C connected to E, and D to E and F. Okay, so this is our connection, and let's see the first step. Okay, so in the first step we are told that A is assigned R, right? That is the information that is given to us in the partial assignment in the question itself. Over here we are given that we have the map coloring problem has already produced a partial assignment A equals to R and B equals B. So we'll first consider step 1, which is just A equals R, and we'll cross out all the colors that are not possible in the different regions. Okay, so A is assigned R, we know that. So let's mark it. Okay, and this cannot be assigned at G or B, it has already been assigned R, and because A has been assigned R, B cannot be assigned R, C cannot be assigned R, and G cannot be assigned R, right? Because all of B, C, and D are adjacent to A. So, and since A is assigned R, B cannot be assigned R, C cannot be assigned R, and D cannot be assigned R. I hope that is clear. Uh, okay. So the next step is B is assigned B. So let's write that down. This is our step 2 now. So B is assigned B. Okay. So G becomes crossed out, and B becomes crossed out from C because B has been assigned B already, right? So we know that since C is connected to B, it cannot be assigned B either, and since C is connected to A, it cannot be assigned R either. So there is only one option left for C to be assigned, which is green, right? Now since C has been assigned G already, we will remove G from E and D, right? Because E and D are both adjacent to C. So again we see that, so next we'll assign a color to this region D, right? Because we were given that a particular order in which we have to assign colors, and these were the alphabetical orders A, B, C, D, E, and F. So again D has only one option, which is blue, so it will go with blue, and because it has been assigned blue, we will cut off blue from E and blue from F, right? So E is now left with only one option, red, Okay, and F is not connected to E, so F can take any color between R and G. Okay, and this is one potential solution to the or the potential solution to the map coloring problem based on the initial partial assignment that was given to us in the question. Okay, so any doubts about this solution? Okay, that's great. Then let's just quickly have a look at the questions that were given over here, just for the sake of completeness. So the algorithm will next assign a value to the variable, and this happens to be C, right? Because we were given an order in which these variables are assigned values, and C is the next value after A and B. What is the value that the algorithm will assign to the above variable? We just saw that C will be assigned G, right? So G will be the solution. Then what are the values in the domain D of the region D at this point after the variable in question 17 was assigned a value? Okay, so this is basically 17, which is this is the question that you were talking about, and this is where C is assigned a particular value. So we just have to look at the corresponding state of the map coloring graph at that point and find the corresponding solution, and we'll see that that will be B. Okay. Similarly, what are the values in the domain E, domain of E, uh, after the variable in question 17 was assigned a value, and you'll see that that will be R and B. And similarly for F, it will be R, B, and G. Okay, so these are the few questions based on this map coloring problem, and for your reference, I've also included a potential worked out solution, which is not done by me. It was done by a previous TA, but yeah, acknowledgements to the previous TA. Um, yeah, so this is essentially the same thing in a more elaborate manner. Um, yeah, sorry about that. So I'll just shift to the solution screen and I'll give you a couple of minutes. Okay, so there are a couple of doubts. Will it ever happen that no color is remaining for a region? It can happen. In that case, there will be no particular solution to that map coloring problem. Okay, so there can be cases where no color is left to be assigned um, to a particular region, and it depends on the way your different regions are connected to each other, right? Um, so just for example, suppose that in this graph, if your F had been connected to E as well, then you couldn't assign R to F because R was connected to E, because F was connected to E and E has been assigned R, right? So you cannot assign R to F. And also suppose if F was connected to C as well, so you cannot assign G to it either. So F will not be left with any assignment of any color, right? So that'll make it inconsistent. So yeah, that case can happen. Um, how to state that? I mean, depends on what question you are asked, right? So if you are asked which color will F take, um, you can say that it's nil. No, F will not be assigned any color. Or if you're asked about any particular stage of your map coloring process in which, let's say, the domain of F is left with some or a subset of the domain, basically you'll have to just mention that subset of the domain. So inconsistent is a term that I used in a non-technical sense. So what exactly that state will be called, you can refer to the video lectures to get a better idea of that. But what I essentially mean to say is that in that case you won't have a solution to your map coloring problem, right? In that context, I said that it will be inconsistent. But yeah, I am not sure whether it's a technical term. For that, I'll encourage you to refer the video lectures. All right, so I'll give you a couple of minutes to go through the solution and then we'll move on to the next part of the session for today. Yeah, sure. We can go ahead. It's great if this is clear. So, yeah, that essentially brings us to an end of the questions for week 12. And yeah, so this is the last slide. All the best for your exams and acknowledgements as usual. But before we end the live session, I want to go over some of the recurring questions or doubts from the previous live sessions. So we'll quickly go over that. So one of the things that was brought up a number of times was savings heuristic, right? So with the help of um, the solutions that we discussed to the greedy heuristic and the nearest neighbor, were any of you able to like understand the savings heuristic a bit better? And if so, would you like to share your thoughts on how to approach the savings heuristic problem? Okay, so no worries. Let me just go over it briefly. So I won't go into the depth or details of the solution. I would encourage you to work it out yourself, but I'll give you an idea about how to go about it. So this is essentially the distance matrix that is given to you, right? Which basically gives you the distance of a city from from different cities. You could think of it in terms of a TSP problem, right? Um, so your end goal is to come up with a tour, and you start with any one of the nodes over here. Let's say you start with B. Okay, that will be your base node for savings heuristic, and then you will draw these kind of an edges for each node other than B, right? So if you start with B as your base node, then you will have an edge going from B to A and A to B. Okay, similarly you will have an edge going from B to C and C to B. Okay, and each of these will have a cost associated with it, right? So I'm not drawing the rest of the edges. There will be something from B to D and D to B as well, B to E and E to B as well, B to G and G to B as well, and B to F and F to B as well, right? So each of these will have two edges connected between them, and what you have to do is in each step you have to choose a pair of these other nodes, right? So for example, you have these A and C nodes. You have to draw some edge between A and C, and when you do that, you have to remove two edges, uh, one that connects A to B and one that connects C to B, right? So you're removing two edges from one that connects A to B, one that connects C to B, and you're replacing that by a connection between A and C, right? And the deciding factor of behind how you choose which nodes to delete, that will be decided by your uh, savings. That is essentially what savings means. Basically, the cost of removal of two edges and being compensated by this additional edge between A and C, or some pair of nodes over here, that is your cost, which will help you decide which two nodes to remove, right? Which two edges to remove. And you will repeat that process for different pairs of nodes until and unless you find a tour that visits each node exactly once and also is the lowest cost. Okay, so if I just have to take one example, let me remove everything so that it becomes a bit clearer. So suppose you take A and B and B to A, right? And from this distance matrix, you know that the cost of going from A to B is 50. So this is 50 and this is 50, right? Let's consider C to B and B to C. And you know the cost of going from B to C is 82. So this is 82 and this is 82, right? So essentially, um, the total cost over here of going from A to B and B to A is 50 plus 50 or 100, right? And the total cost of going from B to C and C to B is 82 plus 82, which is 164. Now suppose you want to add an edge between A and C. So you want to drop one edge going from between A to B and one edge between C to B, right? And the total cost of that would be um, how much? You know that the cost of connecting A and C would be A is connected to C with value 36, right? So the cost would be 50, which is the cost of connecting the edge between A and B, plus 82, cost of connecting B and C, minus the cost of connecting A and C, which is 36, right? So if I am correct, that will come out to be 96. Can someone verify that, please?
It's okay, sir.
Okay. Thanks for confirming. So yeah, so that will have 96 as its cost, as its savings, you could say. You can do the similar kind of a savings value for each pair of edges, right? So here you try to connect A and C. You can also try to connect A with D, right? You can also try to connect A with E, and basically all other pairs of edges, right? So you will have a savings associated with adding a notch with adding an edge between each pair of nodes, right? And then you arrange all those savings or those values in some descending order, and you decide which of them would give you the least cost tour. Okay, that is essentially what you have to do in savings heuristic. Okay, so I think I've taken this example directly from the practice assignment for this particular week, which is week 3, I suppose. There are some questions based on this. You can try to solve them, okay, and that will help you understand the concept much better. So I hope that was clear. All right, so this was one of the recurring issues. Um, Another recurring issue was from the planning uh, week, if I remember correctly. Okay, so we have discussed FSSP in great detail, and BSSP also we kind of covered when when we discussed this backward chaining problem in the last week's live session. So yeah, I don't think I'll go over those once more. Um, no, Ram, 96. The distance between A and C is 36, which is given to you in the distance matrix. 96 is your savings when you remove uh, uh, one of the edges from A to B, one of the edges from B to C, and then you add an edge from A to C. Okay, yeah. So coming back, so yeah, so yeah, BSSP and FSSP, I think we have had discussions on that. You can revisit the previous live session recordings. Let's go over some potential solutions of this block domain problem. Okay, so I think in the last week we had discussed until question 8, if I remember correctly. Yeah, we will cover GSP as well. So Mohan, no, I don't have any plans for mock test. At least I don't have. I'm not sure if NPTEL team is planning for anything like that. It's better if you ask it in the discussion forum or directly to the NPTEL team itself. Okay, so coming back to the questions. All right, so let's see question 9 now. So let BSSP find a valid plan. Which of the following can be the action first added to the plan by the planner? Okay, so BSSP is finding a valid plan, and we have to find which of these actions would be the first that will be added to the plan by the planner, right? Um, so our goal state is to reach a condition where A is on top of D and B is on top of C, right? And the way you can achieve it is by stacking A on D and stacking B on C, right? So if you remember the goal state over here is on B comma C and on A comma D, right? And the way you can achieve either of these is by stack B comma C or stack A comma D, right? Or if you also want to achieve on table D, which would be achieved by the action put down D. So let's see what are our possible solutions. Stack A comma D and stack B comma D would be the answers because those are the first action to be added by BSSP. So remember, BSSP works in a backward manner, right? So put down D would precede, as in here you will have to put down D on the table before you do stack A on D, right? So since we are proceeding in a backward manner, you will have to stack A on D and then add the action of put down D. So the first action that could be added by the planner is either stack A or D, stack A comma D or stack B comma C, right? So I hope that helps. Okay. So the 10th question is, let BSSP find the shortest plan. Which of the following can be the action added last to the plan by the planner? Okay, so the last action that would be added would essentially be the first action that could be added if we moved in the front in the forward direction, right? And for that essentially is if we had to move from the start state, the very first thing that we would do is we would remove D from top of C, right? Because we have to place D on the table, and irrespective of which part of the goal state we want to achieve first, we have to remove D first from top of C. So unstack D comma C will be the last action to be added, right, by BSSP, which is the answer. Okay, so yeah, let's go over this GSP now. So in GSP, after push set executes for the first time, the stack will be. So if you remember in GSP, what we did was we had a stack, right? And we added the different sub goals to the stack in some order that was decided by us, right? If the sub goals were independent, we added the sub goals irrespective of the order. But if the sub goals are dependent, we have to push the elements in the stack in a fashion that makes our solution efficient, right? So and then we take out one of the sub goals from the stack, and then we add appropriate actions to solve that particular sub goal first. So it makes sense that the last element of the stack would be this bottom, which marks the end of stack, right? And then it will have the um, different sub goals added to it, right? Which is basically this is the total sub goal, this is the total goal, and then on top of it we will be adding the different sub goals. Okay, so what will be the order that will be decided, the order of the sub goals? For that we have to see. Um, okay, okay. So here you are trying to solve on A comma D first, on B comma C, and on table D, and that is happening because if you remember, GSP is a combination of the approaches um, of FSSP and BSSP, right? So essentially, what you do is the part where GSP takes inspiration from FSSP is is by using a stack, and the way it takes inspiration from BSSP is by removing one of the subgoals from the stack and then proceeding in a backward manner, right? So yeah, so here the first item that will be pushing onto the stack would be the first sub goal, which is on table D. Then the next thing that will be pushing will be the next sub goal, which is on B comma C, and then the last sub goal, which is on A comma D. So your stack will be something like on A comma D. Behind that will be on B comma C, and then on table D, and then the total sub goal, the compound goal, and then the end marker of the stack. So second option is the correct solution in this case. Yeah, I will zoom in a bit. Okay. So does it mean before E put down there should always be unstack Um, so essentially what you will do is you will first push down the compound goal. Okay, then push down the sub goals. And then whichever sub goal is at the top of the stack, you will try to solve that first. Okay, and in order to solve that, you will pop that. You will add the actions that you want to use to solve that in a backward manner as we did in case of BSSP. Okay, let's have a look at the rest of the questions. Which is the first action that will push to the stack in GSP? So let's have a look at the condition of the stack that is given to us. So you see that on top of the stack you have on a comma t, right? And in order to solve a comma t in a backward manner, you have to push stack a comma t first. So that is your solution. Okay, that is the first action that will push into the stack. What is the first action that will be popped out of the stack? Okay, so if you think about which is the action that will be popped out of the stack, you again have to think in a backward manner, right? So which of these options can you add, can you pop first, or which will be added last to the stack? What do you think? Uh, would it be stack B comma C? It will be pick up A, right? Because see, the first the subgoal that you're trying to solve right now is on A comma T, right? In order to solve A comma T in a backward manner, the first action that you're going to push is stack A comma T. Okay, so stack A comma T will have some other preconditions, right? And in order to solve that, you have to push some other actions, right? So if you look at it in a forward manner, in order to achieve the block A on top of B, the first thing that you have to do is pick up A, right? And so in a backward manner, that will be the last action that will be popped out of the or the first action that will be popped out of the stack in GSP, because that is the first thing that will come up in a backward manner.
So if you create an image of all these things, it will be easy for us to participate.
Sure, I'll draw one quick solution.
Yeah.
Okay, so this is your bottom of the stack. Okay, I'm representing this by dollar. Then you have the compound goal, which basically consists of these three sub goals G1, G2, and G3. Okay, so you have pushed them onto the stack now. Okay, so you have on A comma T, you have on B comma C, and you have put down D. I'm not writing the whole thing. Now that you have pushed all these sub goals onto the stack, next thing that you're going to do is you're going to remove the first subgoal and try to solve that in a backward manner, right? So in a backward manner, if you want to solve on A comma T, what is the immediate action that would lead to on A comma T? It's stack A comma T, right? Right? If you do stack A comma T from some pre-existing state, let's say, that will lead you to on A comma T, right? So you know that you want to achieve that. So then stack A stack A comma T will be added or pushed to your stack. Right, this will again lead to some precondition that will become a subgoal, so that will be pushed again, so on and so forth. And you finally, when you have arrived at a particular plan to solve this part of the subgoal, which is on A comma T, you want to keep popping out actions, right? Because at that point you will only be left with actions, and that will give you a plan. And if you think about it, you are going in a backward manner, right? So you had on A comma T, you chose some action to that led you to on A comma T, then again you chose some state that you pushed, again you chose some action, right? So if you keep doing that, you're proceeding in a backward manner, right? And finally you will reach a state where you will have pickup A, right? Because in order to solve this on A comma D, one of the first things that you have to do is you need to pick up A from somewhere and then keep it on top of D, right? So that will be the first thing that will be popped out of the stack towards the final completion of a subgoal. That is what is essentially asked over here. Okay. So after the first action is added to the plan by the GSP, the updated state S is. Okay. So the first action, once it's added, I think you can work this out on your own. So I won't go into the details of this. Okay. So I think these were the two prominent queries from the previous live sessions, and I hope this helps to some extent. Okay, week 11, 12th question. Let's quickly go to that. Okay, here you are asked, let the forward chaining run to completion for each rule in the KB, count the number of times that rule is generated. So we discussed a very similar problem to this in the previous live session, right? It was exactly same, just the problem, the knowledge base was different, right? So I would encourage you to go back to that question, because if we start solving this right now, it will take a lot of time, right? So try following the template of the problem that we solved in the last live session and then use that. Okay, I hope that will help. If it's still not clear, please do mention it in the discussion forum and request Bhaskaran sir to uh, try to provide some more hints, and I'm sure he'll help. Um, it'll be good if you request for a particular doubt that you're facing as opposed to a complete solution, right? Because that will also help him address what exactly is your query that you're having, right? If you just say that it's confusing and ask him to give the complete solution, that also won't help him understand where exactly are you facing the doubt, right? um, yeah, so what you could do is you could post your whatever solution that you have come up with till now, post that in the discussion forum, and then he can show where exactly is the mistake that is happening if you are getting confused, or where exactly is the issue. Basically, you can have a discussion on that. Okay, so we solved one answer. No, it's not the distance between B and C. The distance between B and C is given over here, right? It's 82. 96 is not the distance between B and C. 96 is your savings when you add the edge between A and C and remove two edges between B and C and A and B. Implies means, you can think of implies as an if and then condition. Okay. So clouds implies rain. If you translate this into a natural language like English, it will mean that if there are clouds, then it will rain. Okay. That is what implies is. All right then. So yeah, that brings us to an end of the questions. And also, yeah, Ram, that is correct. P and Q implies P, which basically means that both P and Q are true. So P itself will also be true. Right? That is what is meant by P and Q implies P. All right. So yeah. So thank you all for attending these live sessions. I hope these were of some help. And yeah, all the best for the exams and whatever you choose to do um, uh, in the coming few years. And yeah, all the best. And yeah, that's about it. See you sometime, some other time.
Thank you, sir.
Thank you so much, sir.
Thank you all for attending.
Can we leave?
Thank you, sir.